Yes, class, is this audible?
Yes, ma'am.
So yes, in the last class, we had started with the chapter electric potential and capacitance. So electric potential we had covered. What is meant by electric potential? Electric potential is basically if I have a test charge with me, a unit positive charge with me, and I have to bring that charge from infinity to a particular point. So all the work done that will be required. That work done is known as electric potential. So electric potential, this is the work done to move a charge from infinity, unit positive test charge to move from infinity to a particular point. So this is the work done. So yes, what was the formula of electric potential due to a point charge? Yes, anyone who remembers it from the previous class? Yes, Maimuna.
Work by Q naught.
Work by Q naught, that is it, work by Q naught. So final formula, that is the potentials formula for general. That is a definition of potential, no? But specifically, if we talk about electric potential due to a point charge, then what will it be?
KQ by R?
KQ by R, correct. KQ by R. So it will be Q divided by 4 pi epsilon naught R. That is electric potential for a point charge. Now see, we had done dipole. So dipole, if you remember, dipole is a set of a positive and a negative charge which are separated from a small distance. Let's say I have this charge plus Q, which is separated from this charge minus Q. And now not taking axial point consideration or not taking equatorial point consideration. If I have to find it out at a general point, at a very general point, this is not a case of axial point, this is not a case of equatorial point. Let's say random point, this is the random point, P point. I have to calculate what is the potential due to this dipole. So firstly, let me take the separation from these 2 points. From plus Q, let's say this is the separation, and from minus Q, this will be the separation. This is at point P. So let's name it even. Let's say this is R1, this is R2. So plus Q is separated from point P and minus Q is separated from point Q. Minus Q, charge minus Q. All right. Now this separation, this is 2A. This is 2A. Now see, I have to find out what is my target to find out the potential. I have to find out the potential at point A. So see, net potential would obviously be given by the net potential because of plus Q. See, now we are not concerned with the direction since potential is a scalar quantity. So you don't require the direction, so you can easily put the magnitude. If Q is the charge, R1 is the separation, and P is the point to which I have to calculate. So Hania, what will be the potential at P due to Q? Yes, Hania?
Ma'am, can you repeat?
Plus Q is the charge. This point P, I have to find out the potential due to this point charge plus Q. R1 is the separation of plus Q to this point P. What will be the potential? In the last class, we did a formula, generalized formula for potential, KQ by R. So potential for plus Q will be what? Honey, try first, try. Wherever you will commit error, I'll help you.
K plus Q by R1.
Not plus, multiply. You have to multiply K with the charge, whatever is the charge. So Q is the charge divided by R1, not added. All right. Now, Hanya, try it for this. Minus Q. Tell me it for minus Q.
K into minus Q by R2.
K into minus Q by R2. So it becomes minus K Q by R2. Why we are considering this minus sign? Because this is a negative charge. So if we take Q by KQ common, KQ will be common, this will be 1 by R1 minus 1 by R2. So see, this will be the resultant potential, but we cannot leave it at this stage, because why? You have no idea about R1 and R2. R1 and R2, we had taken them from our own mind. R1 is a separation of plus Q to that point P, minus Q is being separated from the point P at R2. Now see, if I do some constructions, if I take a perpendicular to this, I want to draw perpendiculars. So let's say I have taken this. Now see, I want to drop some perpendicular from Q and minus Q. So from positive Q, I can drop this perpendicular. Let's say this is point A, this is P already, this is B. So A, P, B. So let's name this perpendicular as C. And this is B, so another perpendicular dropped on it. So these are two perpendiculars that we have dropped on it. This is some construction that we have done. This is point, let's say D. And let's make it as angle theta. This line is making an angle theta with it. All right. So this separation will be what? This will be A by 2 and this separation will be A by 2. We have drawn a bisector to it. Now see, if we write some constructions which are equal. So this point PA means this PA. This is almost equal to PC. This is some of the assumptions. PA is almost equal to PC. All right. So PA will be what? PC is composed of, you have to see, PC is not a single straight line. PC is made by PO plus OC. So PA is what? PA is PO plus OC. This is PO plus OC. PC and PA are almost equal. Okay, that's why we are using this proximal sign. These are almost equal. Now see, PO, this is PO, this whole complete white line, this is PO, and this is your part OC. So that's why I'm saying this is PC. So this whole complete PC has been made up by PO and OC. Now see, PA will be equal to what? PO, let's say this part is small r. PO, let's name PO as small r. Plus OC. PA is already R1. So R plus OC. Now see, if you look at the triangle, in triangle, this ACO, this small triangle. In this small triangle, if you see, if this is theta, then what will be cos theta? In this small triangle. If this is theta, what will be cos theta? Which side upon which side? Yes, cos theta. How do we calculate cos theta? Khalid?
Yes.
Cos theta, look at this triangle, it will be what?
Teacher, CO by AO.
CO by AO, correct. See, cos theta is what? Base by hypotenuse. So base is this OC, hypotenuse is OA. So that's why cos theta will be OC plus AO divided by AO. This is your cos theta. Now see, AO is already A, not A by 2. This will be A because we have taken 2A, no? This will be A only. These two will be A. because 2a has been taken and they have been made on this perpendicular axis. Not perpendicular, this is bisector. So this part will be a and this part will be a. Similarly, this part will be a, this part will be a. So AO will be a. Now see, OC is what? OC is a cos theta from here. Now we have the value of OC. Only OC was missing. So see, R1 is equal to R plus a cos theta. This is your R1. Now see, similarly, PB will almost be equal to PD, where PD is made up of what? Similarly, PD is made up of this point. We are talking about this point. So this will, PD is what? PO minus this portion CD will give us PD. Okay, so this will be, PD will be what? PD will be PO minus OD. Now PB, look at the figure. PB is what? PB is R2 and PO again is small r. So it will be, this will be PB means R2 is equal to, this is R minus OD. Now again, if we look at this triangle, the other triangle which we have drawn, this part, triangle ODB, this triangle. So in this triangle, if I take cos theta, so this is the base, OD is the base, and hypotenuse is again OB. So OD is unknown, now I'll get OD, and OB is again small a. So see, similar to the above triangle, in this triangle, ODQ, cos theta will be OP by OB, which is equal to, now see, OP is what? OP is equal to small r and OB. This is your triangle. Oh, let me draw it again over here. See, this is your angle theta. This is making an angle 90 degree. This is D. This is B. This is O. So this is your base in your this triangle. This is your base, and this side is your hypotenuse. All right. Now hypotenuse in this case is what? This is A. This part is A only. No, 2A is half, becomes A. So in this triangle, OD divided by OB. So OD is what? OD is this part only that we are calculating, R2 plus R. And OB is what? OB is small a. So OD will be what? OD will again be A cos theta. So R2 is equal to R minus A cos theta. Now you have the values of R1 and R2 with you. This was the formula, no, which we had concluded, but we didn't know what is the value of R1 and R2. Now, in terms of dipole, we will be able to calculate. So in terms of dipole, if we are able to calculate, V will be equal to KQ 1 by R1. Now you have the new value of R1 by minus 1 by R2. Now you have the new value of R2 as well. So if we put it in there, we'll get V is equal to, KQ will be common as usual, KQ was common. Now see, this will be 1 by R2 means R plus A cos theta minus 1 by R2. R2 is what? R minus A cos theta. This is potential. Now we just have to simplify it. KQ will be common. Yes, now KQ, this is 1 by R. So we have to take the LCM, R plus A cos theta multiplied by R minus A cos theta. So if we take the LCM, this will be R minus A cos theta. This part, this will be R minus A cos theta minus R plus A cos theta from here, if we take it. Or let's take minus also common. So this will become plus. That will ease our calculation. Divided by, both will get multiplied. R plus A cos theta multiplied by R minus A cos theta. Both of them will get multiplied in this manner. Now see, we just have to solve this. V will be equal to what? This will be equal to KQ will come out, will be common only. Just open the bracket. This will be minus R plus A cos theta. This will be plus R for this plus A cos theta divided by. Now see, A plus B multiplied by A minus B. Are you able to recall this identity? A plus B multiplied by A minus B. Anyone?
1 square minus A cos theta the whole square.
Correct. A square minus B square. A plus B multiplied by A minus B gives what? This gives A square minus B square. So this will be R square minus this whole term. A square cos square theta. We have just squared this and this. Also, minus R and plus R will get cancelled. V will be equal to what? KQ 2A cos theta divided by R square minus A square cos square theta. So Q multiplied by 2A. Are you able to recall this? What is Q multiplied by 2A? What is this Q multiplied by? Dipole, the formula of dipole. Q multiplied by 2A. So V will be equal to KP cos theta divided by R square minus A square cos square theta. So this is the general formula of dipole, of potential due to dipole. Now see why it's a general formula, because we have not taken any particular point, be it axial or equatorial. Now see, we can calculate equatorial and axial from this only. If I tell you, okay, let's do one more thing in this. Ideal dipole approximation, do you remember? We have done it in electric charges and field. What was ideal dipole approximation? Yes, anyone? One assumption, what is that approximation that we should consider? Ideal dipole approximation. Nobody remembers. Size of dipole becomes very small. See, when we had derived electric field due to a dipole, electric field for a dipole, then we had some kind of result similar to this, but we had concluded it into a shorter formula with the help of ideal dipole approximation. In ideal dipole approximation, the size of dipole becomes small. So this separation to the point through the midpoint, this becomes very much greater, means R becomes greater than A. So obviously if R is greater than A, then R square minus A square cos square theta, this will almost be equal to R square. It's like 10 square, that is 100, minus 1 square, that is 1, gives 99. So 99 and 100, these are approximately equal. So instead of writing 99, I can write 100. So instead of writing R square minus A square cos square theta, I can write only R square. So if I put only R square, the general formula, it will become KP cos theta by R square. Now see, from this formula only, I can calculate the two cases that we had done. One is the axial line point, when your point is situated on axial line. Now see, look at this figure. This figure. If I take this point P and I put it in the axial line case, can you tell me what will be theta? Angle between dipole and that point. This theta. See, if I keep on bringing it this, inclining this to here, so that I get the point P over here. Now what will be this theta? Yes, Sarah? If the point, yes, Sarah?
Could you repeat the question?
Yes, see, I'm saying this point is right now over here. This is a general point that I've taken. But what if I bring down this point to this axial line? Axial line, you remember, no? The line on the axis of the dipole. So if I situate this point on the dipole's axis, then what will this angle be? Theta will be. This is the dipole. This is the point line, R. If I bring point like this, what will be the angle then, Sarah? Samaira? In case of axial line, how much?
180.
Not 180, 0 degree. It will be 0 degree. See, 180 degree will be when both the dipole and your point P are situated opposite. In this case, it will be 0 degree. Because see, now this was the point. So this is making some acute angle to which I have calculated. I have taken theta. If I bring this point, let's say this is 30 degree. If I bring this point over here, it will be making some lesser angle, let's say 20 degree, 15 degrees. When I'll bring this point back to this line, then it will be 0 degrees. So your theta is 0. So if your theta is 0, V is equal to Kp cos 0 degree divided by r square. Cos 0 is 1, so you have the final potential for the axial line as Kp by r square. Now the second case is for equatorial line. Now in case of equatorial line, if this is the dipole minus q plus q, this was the point P. Now instead of bringing it to here, I'm moving on the other side. Had it been 30 degree, now it would be at this point some 50 degree, at this point 60 degree. Ultimately, what will be theta at this point? This P,
90.
90 degree. It will be 90 degree. See, how did I choose the angle? This was the dipole. It was making, let's say this was theta. At the axial line, angle is decreasing, angle is decreasing, angle is decreasing. Finally, when the point is on the axial line, the angle is 0 degree. Now, in case of equatorial line, this was the general angle. I'm moving it, moving it, moving it, moving it. This is the equatorial point. So this is what? This is making an angle of 90 degree. So angle is 90 degree. Cos 90 degree is 0. So potential on the equatorial line will be 0. Clear to all of you?
Yes, ma'am.
All right.
Yes.
So note it down, then let's do some questions on it. Okay, Salman. Just take 2 minutes, at least draw the graph portion. Means how these two charges are located on a graph, because coordinates are given to you on the z axis, minus a and plus a. So at least draw the axis, locate the charges, then I'll solve. Take 2 minutes, at least do this work. Locate point A, locate point B, locate point C. See how this will be drawn. See, this is your y-axis, this is your x-axis, and this is your z-axis. So this will be minus y, this is negative. Let's take this as positive. Let's take this as negative and let this be minus x. All right. Now see, you are given charges at point plus q is placed at 0, 0, minus a or plus. Plus q is placed at minus a and minus q is placed at plus a. So see, 0, 0 means x, y are 0. So charges are located at what? Z axis. So plus q is located at minus z, means this separation is a. That's why this coordinate will be 0, 0, y, x is 0, y is 0. And what is the separation? Minus a. Why minus a? Because negative z axis. This is plus q charge. Similarly, on the z-axis, means positive z-axis, you will be having negative q. Why? This point is 0, means x is 0. At this point, there is no component of y, so y is also 0, plus a. Why? Because positive z-axis. So this is what? This is also a. This is the location of the charges. Apart from this, we have for B and C, but that we'll see in the next part only. So regarding the first part, We have the formula. So try to recall the formula. Potential at this point, it is asking us to calculate at which point. Our first part is asking us to calculate 0, 0, z is some point. 0, 0, z means at the z axis only. So VA will be what? Kp cos theta. Since there is no information, we cannot take ideal dipole approximation on our own. This will be r square minus a square cos square theta. So A is what in this case? See, this A is this only, A, that is given to us. The separation of the dipole is 2A, and we take A as it from the origin, means the center. But what is R? R is equal to Z. No, this is given in the question. This is already given in the question. We have to find it at R equals to Z. This is the condition of the question. So simply V will be what? This will be Kp, now cos theta also. Direction of dipole. Dipole is from direction of dipole. Yes. Who remembers the direction of dipole?
Positive to negative.
Anyone would like to correct her? Not positive to negative.
Negative to positive.
Negative to positive. So from the negative to the positive, this is the direction of the dipole. All right, this is the direction of your dipole. From the negative charge to the positive charge. All right, and your point is also located on z axis. So that's why you have cos theta as 0 only. Point is also there, dipole is also there. Axial line case simple. So P will be 0. This will be r square, not r square, z square. Because r is given to us as z only. So this will be z square, and rest of the terms will be z square minus a square. Cos theta is again 0. So this will be the answer of the first part. Is this clear? Yes?
Yes.
Only Khalid?
Yes.
Samaira, Sarah, are you able to understand the first part?
Yes, ma'am.
All right. Okay, fine. So this is a formula-based question only, no? Your point is given to you as the R or the separation, the point is given to you as Z. So whatever formula you have done, you have just put Z instead of it. Now see, the second part is very easy now. B is X comma Y comma 0. Means a point where there is no component of z-axis, but it has a part of x-axis, it has the value of y-axis. So it means it is in xy plane. If you have it point, let's say this is your point. This is your xy plane and you have the point, you have chosen the point B point. This is x, means it has some value on x-axis, comma y means a value from the y-axis, 0 means no component of z-axis. Now see, you don't even need to calculate anything in this part. It's an xy plane. Dipole is in z-axis. Angle 90 degree. Your point is now on the xy plane. XY plane, and your axis is like this. Z-axis means the dipole which is situated in the z-axis. So your point is on the equatorial line. This is your dipole. Now your point is on the XY plane. So if your dipole is on the equatorial line or it is making an angle of 90 degrees, then do you even need to calculate it? VV will directly be 0. Reason? 90 degrees. Because why? Because this point, this B point, that is x comma y comma 0, this is a case of equatorial line. Now see the other point that it has given to you in the same question only, x 0 comma 0. This point is C, x 0 comma 0. C means it is located on x-axis. This point is C. It has some value on x-axis, x, comma 0, no component of y. comma 0, no component of z. Now see, this point is still lying on x-axis. Your dipole is on z-axis. Z-axis and x-axis. What is the angle? What is the angle between z-axis and x-axis, class? Yes. Yes, Khalid.
Yes, teacher, what's the question again?
Angle between z-axis and x-axis. What is the angle?
120?
All the three axes are perpendicular to each other. This is your
90.
y-axis. This definitely 90 degree. This is your z-axis. That's why we draw the graphs in this manner. No, for all those who are getting different angles like 45, like 60 degree. See, understand, all the three graphs means all the three axes are perpendicular to each other. You always draw x and y axis in this manner only. Why? Because the angle is 90 degree. If you draw a graph between z and x, this will also be 90 degree. All the three axes are perpendicular to each other. So if the location of the point is what? The location of the point is x, 0, 0, this point. Now the angle, don't look it in this manner that it is looking inclined and the point is in this. So it will be some 60 degree or 45 degree. You have to see the axis. This representation of diagonal is showing that z-axis going inwards, means into your notebook. Y is upwards. Z-axis is going into your notebooks. So we cannot draw it in this manner. So that's why we draw it in this shifting manner, tilting manner. Otherwise, all the three axes are perpendicular. Don't think that this angle is something, this angle. This is 90 degree. It's just that if this is the y-axis, z-axis in this manner. So in order to show it diagrammatically, we draw it in this manner, inclined, like this. Otherwise, all are 90 at 90 degree. So VC will also be 0 because this point is again, now it becomes the case of equatorial. The angle is 90 degree. So C point x, 0, 0, this is an equatorial point. Equatorial point. Now see the third part. Third part is asking you the work done. Work done in carrying proton from B to C. So tell me, is there any potential in B or C? Did we get any value of potential? Look, the answer is in front of you. We didn't get any potential, no, because VB and VC both came out to be 0. So the formula of work done, if you remember, we had done work done in carrying charge from point B to C is the potential difference, VC minus VB, final minus initial, multiplied whatever is the charge. Now VC is also 0, VB is also 0. So work done to carry the charge from B point to C point will also be 0. And the last part, fourth part. In the fourth part, it is asking you, does work done depend on the potential between B and C? See, work done is path independent. So electric field is a conservative force. So that's why your work done is path independent. So it doesn't matter, it does not depend. It just depends on the initial and final point. So work done is path independent. The reason is that electric field is conservative. Clear? Work done is path independent, that you already know that it depends on the initial and final point. Main thing you have to remember, you have to identify the location of the point. It will give you random points like this, the way we had been doing B point, C point, random points with random coordinates. You have to first identify this is which case. Is it an axial case? Is it an equatorial case? Or it is a general line case? All right. And don't get confused with this angle. All these are perpendicular, all the three. of them, y-axis, z-axis, and x-axis. All three are perpendicular to each other. So even negative z-axis and positive x-axis, positive z-axis and negative y-axis, any of these will be perpendicular to each other.
Ma'am, can you show the question also? Yeah, okay, ma'am.
If anyone of you faces any difficulty in the solution of this, just ask me. Salman, I think you were not there when we were discussing. So if you have any difficulties or issues, just ask me there and there.
Yeah, okay, ma'am.
Done?
Ma'am, can you say again why V uh, VC is 0?
Okay, VC and VB. Regarding VC and VB, see, Salman, just focus on the coordinates that are provided to you. All right. See, B's coordinate is what? X comma Y comma 0. In your graphs, when do you write X comma Y comma 0? When you don't have any z-axis component that shows 0 of z-axis. X comma Y means it has the value of x-axis. Like this, some value of x-axis from the graph and some value of y-axis from the y-coordinate. So in xy plane, your B is 9. So if your plane is this xy plane, perpendicular to xy plane is your which axis? Z-axis. And dipole is located at which axis? Z-axis. So this xy plane is making an angle of 90 degree with z-axis, means your point B located on xy plane is making an angle of 90 degree with what? The dipole. So theta is 90 and cos 90 is 0. So you get the dipole as 0. Similarly is the case of C. X comma 0 comma 0. In case of x comma 0 comma 0, it means the point is situated on the x-axis only. That's why you have no component of y and z. So see, your x-axis is there. You have your y-axis as well. Y-axis is there. Z-axis is there. So this is your z-axis pointing outwards, your x-axis. Z-axis and x-axis both make an angle of 90 degree again. All the three axes make an angle of 90 degree. So VC is also located at such a point which is making angle of 90 degree. And whenever you have theta as 90, that is equatorial case, meaning cos 90 is 0. So potential becomes 0. Yes, Arman?
Yes, ma'am.
So everyone has noted it down, or is anybody writing? I think everybody has noted it down. All right. So if anybody is writing, just text me. Otherwise, let's do one more topic. This topic is the relationship between electric field, relation between electric field and potential. How can we connect electric field and potential together? Now see, if these are electric field lines, random electric field lines I've taken, and the tangent to it gives electric field, this angle I've taken it as theta. All right. So a charge I have taken at point A. This point A, I have taken a charge. And the separation of this point A to the center means this point B, or I have taken some point B over this curve. This is the electric field line. Electric field line. So I've taken 2 points A and B, and the direction of electric field can be given by the tangent. I have just these two now, A and B point. Now a work done in carrying charge, from A to B. So let's say this distance AB, this is dr. So as to ease our calculation, what is the general formula of work done that you have studied? I think we have revised it on Monday as well. General formula of work done from your previous class, 11th. Yes, work done. Force into displacement. So work done will again be force into displacement. Now see, force in this case, charge is Q, electric field is E, F is equal to QE. Force is equal to what? Product of electric field and the charge. The distance means the displacement is this only from A to B. So A to B, this curve is, this point is B, this point is A. But this displacement is dr, no? So displacement is dr. So work done becomes what? Work done becomes QE dr. All right, QE dr. Now see, this is one formula of work done. Other formula of work done that we have studied, work done in carrying this charge, regarding the potential when we include work done can also, this is one of the equations. Let's name this equation as one equation. Now work done is what? Work done is also Q charge multiplied by dV. dV is the potential. So it means both of these work done are equal. So if I equate all these two work done, these two means this is through potential, through the definition of potential. I've got this equation. Yesterday, on Monday only we did, no, charge multiplied by the change in potential. So QEDR is equal to what? QdV. So Q gets cancelled, electric field becomes dV by dr. And we have a negative sign also. So what is the significance of this negative sign, or what is this negative sign, that I'll tell you. But for now, remember dV by dr means differentiation of potential. Now this is potential gradient. Whenever anything gets divided by the distance, that we call it as gradient. If you remember, if we divide anything by time, we call it as rate. Like velocity is what? Distance divided by time. So we call velocity as rate of change of distance, displacement. So in this case, what is, we don't have time. Had there been time instead of r, we would have written rate of potential, rate of change of potential. But now in this case, potential is getting divided by r. It means the gradient, it is getting divided by the gradient. So we call this as potential gradient. This, let me write it down. This E is equal to dV by dr. This part, this is called, this is what? This is the change in potential. See, if you have any change in any quantity with respect to time, we call it as rate. Like rate of change of velocity is acceleration. It means velocity divided by time is acceleration. That's why we have used the word rate. In case of gradient, we have displacement or distance, this quantity. So change of potential, rate of change of potential, this becomes what? So change in potential with respect to position. Change in potential with respect to position, this is called as gradient. This is known as gradient, rate of change of potential. Now see, you can have all the potentials for different axes. Like if you have electric field for x-axis, you can write it in this manner. Ex is equal to minus dV by dx. If you have Ey, you can calculate Ey, which is equal to minus dV by dy, differentiation of potential with respect to y. If you have z-axis, then Ez, electric field on the z-axis, will be differentiation of potential with respect to z-axis. And if you have to find out the net field, this will be equal to vector sum Ex plus Ey plus Ez. Ey plus Ez plus Ex, whatever field you are getting. Now see, minus sign. Yes, I have not told you what is the significance of this minus sign, negative sign, by, or how do we write this minus sign. All right. So see, minus sign is what? Significance. Significance of negative sign. Significance of this negative sign. What is meant by this negative sign? See, E is equal to minus dV by dr. The statement is given in your NCERT as well. E is equal to dV by dr. This means negative. This shows that electric field, or the direction of electric field, see, negative or positive sign always indicates the direction. So direction of electric field is where potential decreases. This is along the direction of field where potential decreases. So potential decreases. This statement is mentioned in your NCERT as well. Two statements I think are mentioned. One is that electric field is rate of change of potential, not rate, change of potential with respect to position, that is gradient. And second important statement is this only, direction of electric field is where potential decreases. So this negative sign shows a long direction of electric field where potential decreases, where a long direction of electric field where potential decreases. So wherever there is less potential, you have more of electric field. It gets inverse. Now see, if you have a random, if I give you some random question, like if I have at this point A, let's take 5 volt. At this point, let's take 2 volt. All right. This is electric field E. All right. Now this is E, this is 2 volt, this is 5 volt. Electric field's direction will be towards 2 volt. Why? Because lesser volt is what? 5 volt or 2 volt? 2 volt. So electric field will be in the direction of 2 volt. This is what is meant by this negative state. Also, one thing that we were discussing, dx over dv over dx, v over dy, dv over dz. Sometimes you have to use partial differentiation. If you have y, you have dv over d, this is y, no? And dz is partial differentiation. So we'll do how to apply partial differentiation. If sometimes you need to apply partial differentiation. So we'll do partial derivative, how to calculate. First note down this, then we'll do then questions. Just note down this part, relationship between electric field and voltage. So from here only, our relation, I told you in the initial class only, electric field is also given by Newton per Coulomb, and also electric field is given by volt per meter. So volt per meter is from this formula, E is equal to V by R, and N by C is force by charge.
Ma'am, could you scroll down?
Everyone has written this?
No, ma'am. Wait 1 minute.
Okay.
Done, ma'am.
Now see, if V is equal to KQ by X, what is electric field? So V is KQ by X. Electric field is what? Electric field is minus dV by dx. So simple difference, again, as I've told you in this chapter, differentiation and integration are used a lot. So electric field will be what? Minus d over dx. V, you have KQ by X. Now differentiating it. K is a constant that will come out. KQ, these are constant, minus KQ will come out. You have to differentiate 1 by X dx by 1 by x. You have to differentiate this. So x is in the denominator. Let's bring it in the numerator. This will be x to the power minus 1 dx. Now, how do we differentiate it? First, whatever is the power comes out. So electric field will be what? Minus kq. This is the constant. Leave it. Differentiating this, focus on this part, how to differentiate it. Your power comes out, means power gets multiplied. The power that comes out means it gets multiplied. X to the power n is what? N comes out means gets multiplied, and what happens to the power? It gets subtracted by 1. So minus 1, minus 2. You have to multiply this term. So minus 1 multiplied by this minus sign makes it positive. KQ, x to the power minus 2. Now see, putting x back to the denominator, this becomes KQ by x squared. So this was the formula of electric field. Now with the help of this, we are able to clarify and confirm that yes, electric field and potential. And from here also, if you integrate it, you get potential back. And if you differentiate it, you get electric field back, because differentiation and integration are inverse operations. So with the help of electric fields integration, you get potential back, and if you differentiate potential, you get electric field back. This was the formula of electric field, KQ by x square, if potential is KQ by x. So note it down. Now I'm giving you another question that you all should try and answer. Simple derivation. Not derivation, sorry, differentiation, based on simple differentiation. I'll be giving you value of voltage. You have to tell me what is the value of electric field. So see, I have given you V. You have to find electric field at x equals to 2 meter. So first differentiate it. Whatever is left, it will be left with x. Put x as 2. See what's the numerical value you are getting. Everyone should try this question, because 3x cube, this is the simplest question that is possible in differentiation. So all of you submit your answers quickly after copying it down. Khalid, what is the value of electric field that you are getting?
9/16.
9/16. There is no x. Just check it once again. Check your calculations once again. Sarah, it's correct. Your answer is correct, Sarah. Rest of you others also submit. Only 2 students have tried the question. Hania, Memuna, Salman, Samaira. Submit your answers quickly. This does not involve much of your calculation. 3x cube, you can even differentiate it directly. Okay, Samaira has submitted. Samaira, Khalid, and Sarah. Only these 3 have given their answers. Memuna, submit your answer.
Yes, teacher, one second.
All right. Okay, Hania has also given. Salman and Samaira, both of you also try this because this is
Yes,
very
ma'am.
easy. Okay. Okay, Samaira has given. Samaira has given. Okay, so Memuna has also submitted the answer. Let's discuss it then. See, V is what? V is 3x cube. Electric field is minus dV by dx. It means you have to differentiate 3x cube. You have to differentiate this 3x cube. Now see, 3 is a constant. Let the 3 be as it is. Whatever is the power x cube, this is your n now. X to the power n. X to the power n becomes nx n to the power minus 1. N is what? N is your power. And here n is 3. This 3. X to the power n minus 1. 3 minus 1 is what? 2. This is 3x square. So 3 into 3 is 9x square with a negative sign. So electric field is what? Electric field is minus 9x square. And x is given to you as 2. So put the value of x. Electric field will be minus 9, 2 square. This will be minus 9 multiplied by 4. That is minus 36. So electric field will be minus 36 volt per meter. And this correct answer has been submitted by only Sarah. Now Khalid, yes. All right, note it down. Okay, so all those who have to pray, just take a break of 5 minutes, then I'll continue. Yes, rest of you submit an answer of this question. The separation between the points is 10 meter. The potential difference is 20 volts. What will be the electric field? The simplest question possible from this topic. Everyone should be able to answer. Distance is given, potential is given. What is the electric field? Camera, your only magnitude is correct. Check the complete formula. See, this will be equal to what? Change in potential, the potential difference. Potential difference is given to you as 20 volts. The distance, change in the distance, this is 10 meters. Electric field is what? Electric field is minus delta V by delta R, or change in potential by change in distance. This will be minus 20 divided by 10. So electric field will be minus 2 volt per meter. Memona, is this clear now? Yes, Salman.
Yes, teacher.
Your answer is correct. Okay, don't forget the negative sign in case in this, because we have a significance of this, no? So consider this negative sign. Okay, Salman, your answer is right. Yes, Khatib. Correct. Just note down these 3 lines, all those who have not written. Then I'll let you know how do we solve partial differentiation. If by any chance you get the question on partial differentiation, how to do it. See, partial differentiation, let's do it through the help of an example. Let's say V is x square y z square. This is your potential. In case of partial differentiation, if I am differentiating Ex, so partial differentiation of dV, dV means your potential, by dx, this will be C what? When you are getting Ex, you will differentiate y x axis component only, x only. Y and z will act as a constant to you. See, if y is a constant, constant comes out, it gets multiplied. If z is a constant, means z square is a constant, so that will also come out. Now you just have to differentiate x square. In x, y, z square, these two act as constants when we are differentiating electric field for x-axis. So you just have to differentiate x square. X to the power n is what? N x n to the power minus 1. N is 2. X to the power 2 minus 1 is 1. So this becomes 2x. This is your x-axis. Now, if you have to differentiate it for y-axis, Ey will be what? Partial differentiation, negative sign will be there. Negative sign will be there. All right, negative sign will be there. Because this will be minus partial differentiation of this. Now, x and z will be the constant when you are differentiating y. So what was our number? X square, y, z square. So x and z are constant, means x and z, x square minus sign z square. This is already a constant for you, so all the constant comes out. What is left? Differentiation of y, dy over dy, it's what? It's 1. Yesterday we have seen only dy over, on Monday we have seen dy over dy is what? 1. So this will be, that's it. This will be for y-axis. Electric field for z-axis. Partial differentiation of potential with respect to the z-axis. Now x and y, the other two terms apart from this will act as constant. What was our number? X square y z square. This was the polynomial that we were given. X and y are now the constant. So immediately write with a negative sign x square y. Now differentiate z square. Z to the power n will be what? Nz to the power n minus 1. N is 2. Z to the power 2 minus 1. 2 minus 1 is what? 1. So this becomes 2z. So if you have to know what is the net electric field, that will be minus, what was that? yz square 2x minus yz square 2x I cap plus minus x square, this is your one term, minus x square z square j cap plus minus x square y 2z k cap. This is how you get the net electric field. Now the question can extend up along with this also. It can extend more. How? It can ask you calculate electric field at 1, 1, 1. So what you do? Just put all the values of, I'm just taking an example, x as 1, y as 1, z as 1. In your equation, what you are getting? x1, y1, z1, and y1, x1, z1. So it becomes minus 2 cap. From here, x square z square means minus 1 j cap. From here, x square y z all are 1, it will be minus 2 k cap. Whatever is the question, at 0, 0, 0, so electric field will be 0. 1, 0, 2, any point it will give you, so you can put the values. If it asks you the magnitude, then magnitude of electric field also you can calculate. How do you calculate magnitude of a vector? By taking the square of all the coefficients and adding them. This will give you the magnitude. So in any form, if the questions come, now will you be able to answer? Yes or no? Yes, class?
Yes.
Yes.
All right. So note this down. If you have any doubts in partial differentiation, just ask me. Done? Just let me know when you all have written. At least write done, or you can unmute yourself. Okay, so most of you are done with the writing part. Just the last topic for today's class. Then we'll wrap up the class. Equipotential surface. This is a very, very small theoretical topic, and from the name also you can figure out. Equipotential means what? Potential is equal. So if you have a surface, this equipotential is that surface at which every point has same potential. Equipotential means what? Equal potential. So a point, a surface which has potential at all of its surface same. Like if I give you an example, I have taken a sphere and the charge on the sphere is Q. Radius of the sphere is capital R. Okay. And I tell you that the potential at this surface is at this sphere, on this sphere, this is 2 volts. Potential, if you take this point A, here the potential is 2 volt. if you take up the potential here, VB, here the potential is 2 volt. If you take this point, VC, the potential is 2 volt. Reason is that potential will be given by KQ by capital R. K is a constant, 9 into 10 to the power 9. Charge is same for the whole sphere. Radii at every point will be capital R only, even if you take this point, this point, this point, radii will be the same. So all the points, any point if you take, potential will be 2 volt only. 2 volt is just a random number that I have taken from myself. If you get such a case, then we call the surface as an equipotential surface. Or random, not necessary to be it a sphere, any random surface, A point, B point, C point, all these surfaces. If I say VA is equal to VB is equal to VC, then your surface is an equipotential surface already. No need to be symmetrical. It has certain properties. Let me discuss the properties as well, then only it will get clearer what is meant by it. But just remember, equipotential surface is what? Means what? Equal potential surfaces. So let's discuss the properties as well. What is meant by equipotential surfaces? Properties of it. So first property is the definition that the potential at every point is same. Potential at every point on what? On the equipotential surface is the same. So if you have any kind of asymmetrical figure like this, having all the sides non-equal, then also A point, B point, C point, D point, any point, VA will be equal to VB equal to VC equal to VD if it's an equipotential surface. This is the first property, which is the definition only, definition of equipotential surface. Now see, the second property is a very important property because this has come a lot of times in your previous year questions, even of your board examination, of your entrances. It's a very easy property, but it has appeared a lot of time. See, the second property says what? If you remember, work done was what? Charge multiplied by the change in potential, delta V. Like if this is the case, I have to move it from A to B, then change in potential will be what? A to B means VB minus VA. Now see, VB is also same, VA is also same, both are same, VA and VB have the same magnitude. So if you subtract the same quantities, you will get 0. So there is no change in potential, no changes in potential. Why? Because the potential is same. That's the condition of a surface for being called as an equipotential surface. There is no change in the potential. So no changes in potential means delta V is 0. Why? Because VA minus VB or any, this will be 0. Because VA, VB, all these points are same. So this will be 0. So if delta V is 0, whatever be the value of charge, will we get any work done? What will be the magnitude of work done?
0.
0. Correct, Samira. This will be 0 because charge will get multiplied by it only. Charge gets multiplied by the potential and the voltage. That will be again 0. This was the second property. Now the third property. The very short properties are there. Now see, if you take an equipotential surface, let's say this is an equipotential surface. Electric field is always perpendicular to an equipotential surface. If this is your equipotential surface, this will be the direction of electric field. This is dr or in point. Electric field will always be at 90 degrees. Electric field will be at always 90 degrees. Remember. So electric field is perpendicular electric field is perpendicular to the equipotential surface. Equipotential surface means what? A surface which has potential, all same potential at every point of it. So electric field is always perpendicular to it. All right, electric field is perpendicular. Now see, in the regions of strong electric field, if you have strong electric field, then your equipotential surfaces are closer. Means all closely packed equipotential surfaces, that gives you strength of electric field. If you remember electric field lines, this was the same case. If electric field lines are together, that gives strong electric field. If electric field lines are kept far apart, then it means weaker electric field. Similarly, if you have weak electric field, then equipotential surfaces are far apart comparatively, not much, comparatively. Let me write comparatively. Comparatively, these are far apart. Like if, let me give you an example. These are some equipotential surfaces. So this is region 1, this is region 2. Equipotential surfaces are closer in this region. This is the distance. Whereas this is the distance for electric field in the second region. So you can simply look at the equipotential surfaces and figure it out, the comparison between the electric fields. Electric field in 1 will definitely be greater than the strength of electric field in region 2. Reason being that equipotential surfaces are kept together and equipotential surfaces are comparatively far from each other when this is the case. You don't even need to learn this. The logic for it, I try to identify the logic. Electric field is what? Electric field is inversely proportional to dr. Now see, if distance increases, electric field should have increased. No, according to this, if electric field should decrease. Inversely proportional, no. According to it, if distance increases, then electric field decreases, or if your distance decreases, then electric field increases. This is the reason why equipotential surfaces, if they are kept together, they show strong electric field, and if they are kept far apart, they show different electric field. So these are the properties of equipotential surfaces, very basic properties. Now see, apart from these properties, what you have to remember in case of equipotential surface is that how to draw this. If you have to draw them, how will you draw? So if you have an isolated charge, isolated point charge. If you have isolated point charge, how will you draw the equipotential surface? See, plus Q is there. This will be the one equipotential surface. This will be another equipotential surface. This will be another equipotential surfaces. So let's say some electric field is there and it has separation R. This is small r. So this will be equipotential surface for an isolated point charge. These are the equipotential surfaces. Equipotential surfaces. Now see, this is a single positive charge. What if you have 2 point charges? You can get 2 point charges. If you have 2 point charges, 2 positive charges. Let's take both of them as positive charges. So what will happen? There will be repulsion. Plus Q is there, plus Q is there, there will be repulsion. So equipotential surfaces around this charge, as you will go apart, means if you will keep on drawing more equipotential surfaces, they will be closer here, but they will be far away from here. They will be closer here, but far away from the side which is pointing this charge. Again, it will be closer here, but far away from here, in this manner. This is why, because of the reason that 2 positive charges will be repelling each other. In this point, what will happen? One electric field will be here, one electric field will be here. Both will be in opposite direction. Alright, so if you have 2 point charges, 2 positive or 2 negative charges, this is the case. But if you have unlike charges, means if you have both the charges together means dipole. Negative charges, positive charges, the second one is the same. If you have positive and negative, then what will you do? In this case, attraction will occur, attraction between charges. So equipotential surface, instead of getting far away from each other, they will be inclined. Now here they will be closer and here they will be far. In this region, equipotential surfaces will be closer, here they will be away. Again, they will be closer in this region and they will be away. In this region, they will be closer and they will be away in this region. This is what is meant by a dipole. If you are asked to draw electric equipotential surfaces along some axis, let's say it has given you electric field uniform, let's say uniform electric field along x-axis. So what you'll do, if you have such a case, uniform electric field is there. So if these are your electric field lines, x-axis, then draw equipotential surfaces in this manner. One equipotential surface is separated from the other one at a constant distance. Then other equipotential surface is separated at a constant distance. When you have electric field to draw on, when you have electric field as non-uniform, same question for non-uniform electric field. Non-uniform electric field. Then how will you draw? These will remain the same. But now, as I've told you, non-uniform electric field means what? One is having another's, means where equipotential surfaces are closer, that depicts that electric field is stronger. So let's say electric field is stronger over here, this region. So whenever this question comes, then draw equipotential surfaces two closer and draw the third one a little away from it. That will show that electric field is non-uniform. So clear equipotential surface. This topic is clear to all of you. Salman,
Yes.
Sarah.
Yes, ma'am.
Okay.
Yes.
All right. So just note down this as well.
Ma'am, can you show the third point again? Yeah, okay, ma'am.
Yes, done.